In this problem, we're asked to calculate the pH of a weak acid solution. So the first thing I'm going to do is build an ice table. So the reaction that we have, hypochlorous acid, is HClO. It's going to be reacting with water. To form hydronium ion. And the hypochlorite ion. So initially we have 0.1 molar hypochlorous acid. We don't worry about the water because it's a liquid. And I don't have any hydronium ion or hypochlorite ion. The reaction is going to be moving to the right because I have reactants and I don't have any products. So I'm going to call the change in the reactant minus X. I'll call the change in the products plus X. And because the coefficients in our reaction are all 1 to 1 to 1, the change is minus 1x, plus 1x, and plus 1x. So the equilibrium row of the table is just the initial plus the change. So I have 0.100 minus x for the equilibrium concentration of the acid. And then the equilibrium concentrations of the hydronium ion and the hypochlorite ion are just 0 plus x or x. Now before I can plug this into my equilibrium constant expression and use K to find x, I need to go from the pKa to the Ka. So remember, to get the Ka is going to be 10 to the negative pKa, or in this case, 10 to the negative 7.54. So that means our equilibrium constant, our acid dissociation constant, is 2.88 times 10 to the minus 8. So on the next slide, I'll go ahead and plug this into my equilibrium constant expression. And at the top, I've just typed up the ice table that we made on the previous slide. And so when I go ahead and plug everything into my equilibrium constant expression, I have that the Ka is 2.88 times 10 to the minus 8. That's equal to the concentration of H3O plus to the first power, concentration of ClO minus to the first power, over 0.100 minus x. Now, we might end up with a quadratic equation we're going to have to solve because I'll have an x squared term, I'll have an x term, but because our equilibrium constant is small, we can use the K is small approximation that we learned when we first learned about equilibrium, and so that means that X is going to be very small. The reaction is not going to go very far toward the product side to get to equilibrium. That means that X is going to be very small relative to 0.1. So that means 0.1 minus X is basically just going to be 0.1, and I can ignore this minus X in the denominator. And so I can rewrite that right-hand side of the equation as x squared over 0.1. So it becomes much easier to solve for x now. So to solve for x, I just multiply both sides of my equation by 0.1. So the left-hand side becomes 2.88 times 10 to the minus 9 is equal to x squared. And I just have to take the square root of both sides, and I end up with x is equal to 5.37 times 10 to the minus 5 molar. So in the statement of the problem, we were asked to calculate the hydronium ion concentration, and since the hydronium ion concentration is x, I can go ahead and say that the concentration of H3O plus is 5.37 times 10 to the minus 5 molar. And so that's the first part of the answer. The problem also asks us to calculate the pH. So let me do that on the next slide. But before we do that, whenever we use the K is equal to small approximation to ignore the X in our equation here, we want to double check it at the end of the problem to make sure that x was in fact small. So we want to be sure that the change is less than 5% of the initial concentration. So when I do that, in my check, I'll do 5.37 times 10 to the minus 5 over the initial concentration times 100. And when I do that, I get 0.0537%. So we said that it's okay to make this approximation when the change is less than 5% of the initial concentration, and so we're much less than that. We're 0.05% less, and so this approximation was okay to make. Okay, so to calculate pH, we'll use that pH is the negative log of the hydronium ion concentration. So in this case, pH is just the negative log of 5.37 times 10 to the minus 5, or pH is equal to 4.27. And we're done.